Yeah, I'm Gary Schellhorn, Public Works Director, and we're out at the construction trailer for our new wastewater treatment plant. And it's about a $40 million project that we've got going on for the treatment plant itself. And the sewer mains that will connect this plant with our existing one and with the City of Comanche and Lowmore is about another $10 million. So altogether it's about a $50 million project. And behind me you'll see a drawing up here that kind of lays out the various processes of the treatment plant. This one here is a solids handling pad. We've got digesters here. This is the headworks pumping station. This is the aeration basin where the actual process takes place. More than anything else, this is where all the biological activity takes place. And then we have final clarifiers for the settling of the solids, final settling, and then we have a final effluent pump station that will pump it back to the river.
Could you tell us where, when this is in operation, where the sewage comes in, and then which of these, well, the sequence that it goes through and what each one actually does to the sewage?
Sure. When the sewage comes in, it'll come in through pipelines out here, come into this headworks building, gets pumped then through these basins. It will stay in these basins for all of the biological process to happen, the vast majority of it.
And what is the biological process?
It's just basically we pump a lot of air into the wastewater, and the air literally oxidizes or consumes the bacteria in the wastewater. The solids that settle out here, the heavier solids, will be pumped over here to the digesters for further processing, and then we eventually land apply those solids.
And why are they called digesters?
Because we have further digestion, in other words, continued organic activity in those buildings. In other words, digesting more of the solids.
So it's much like in your stomach where the solids go through a process where they're broken down.
Lower stomach.
Yeah, well, okay.
This one would be the stomach, this would be the lower stomach.
Okay.
And then after the water comes out of the aeration basins, there's still a small amount of solids in it. It goes to final clarifiers where that final solids will settle out, the very light solids. There's a long detention time. The water will just look like it's just setting in there even though it's moving very slowly. But the solids that will come off the bottom again get pumped back over here for digestion and further treatment. And then the clear water will come out to the pump station and be pumped back to the river.
Okay. Shall we go out and take a look at what's actually being done outside?
You bet.
Go.
Alrighty, we're in the headworks building that we talked about in the trailer. And this pit down in front of me is where the actual raw sewage will come into through these various pipes. And then to my left you'll see 3 gate wells that open up into channels that go into the next process. And you'll see 2 big bar screens there. Those bar screens will collect all the rags and debris that we don't want into the process that come through the system.
Now you have, it looks like 3 big intakes here. Is that right? 3?
Yes, there are. Yeah, we can talk about that.
And where? And why not explain where they're coming from? Why we have 3?
Well, you'll see we have multiple intake pipes coming into this wet well, and the purpose of that is that a wastewater plant doesn't have the same amount of flow all the time, so that during
top again.
Okay, this is the wet well, the very first part of the wastewater plant. All of the wastewater from the City of Clinton, City of Comanche, Lowmore, and our future industrial park out in the western part of town will come into this wet well. The multiple pipes are in here because every wastewater plant has the flow varies during the day from highs to lows or from wet weather to dry weather. So we have, in any pipe we can only flow so much liquid. So obviously at low flow it'll come through 1 or 2 pipes, at higher flow it'll come through multiple pipes. That's the purpose of those pipes. To the left of me is 3 gate wells that we will operate, that will send it through the 2 bar screens and then onward to grit collection. But these gate wells will go down into channels that will channel the flow in past the bar screens that you see, and then we'll step outside and you'll see the grit removal units. These 2 two pieces of equipment behind me are called bar screens, and the raw wastewater will come into those bar screens. Those screens are fairly fine. They're less than a 1/4 inch spaces in those. That will collect all the debris, paper products, and debris that we don't want into the wastewater stream. And you'll see there's augers that come off each one that will then drop all of that waste product down into a dumpster for landfill. Standing next to our grit auger, which on the outside of this building are two teacup type separators where the sand and the fine grit that's in wastewater that it picks up from streets, runoff and things like that, but other just fine silt, that gets separated from the waste stream. It's pumped into this auger system, and then it's augered up and goes into the same dumpster as the bar screen debris.
Hold on. Okay.
We're standing on top of the grit removal units. You'll notice in front of me is the drive unit for what below this concrete structure is the teacup grit separator, and behind me is these gate valves that we can lower and either go to one or the other or both of these teacup separators with the flow. The flow then continues out of this structure, goes underground into that next structure, the oxidation ditches.
And that's where we're headed now.
Yep.
Huh? Fire away.
We're standing on top of the influent structure for the oxidation ditches. This structure right here with all these different gate wells is where the flow comes from the headworks building where we remove the rags and the debris and the grit. Then it comes over to here where in these various gate wells we can separate the flow out to these 3 different basins that we have behind us. There's also several smaller basins at the front of the oxidation ditches that are used for phosphorus removal and advanced treatment of wastewater.
So how deep are these wells?
18 feet.
18 feet. And how big is the pipe coming in? Looks big.
36 inches.
And this is actually going out from here, right?
Well, it'll go into there and then split. You can see where it kind of will split into the 2 basins. And you can see we've got overflow points and underneath for the advanced treatment for phosphorus removal. An interesting thing to note is this headwork structure behind us over here, and you'll notice the curved walls, and it's about 30 foot deep into the ground. There's a lot of various channels in it that are all formed out of concrete. Interestingly enough, that took as much to build as some of the biggest structures we have, because these are all just flat walls and are easy to form up and pour. We're standing on top of the oxidation ditches, which is where all the biological activity takes place in the treatment plant. And to my left, you can look into this first basin, and you can see all the little white discs. Those are actually the aerators. We pump air through those. We'll get into the building after a while with the blowers. But all we really add to wastewater to treatment is oxygen. We pump massive amounts of oxygen into the wastewater, and that is what actually treats the wastewater. You can see 3 flight mixers, just rotary mixers. In each one of these basins, the flow goes around like a racetrack, and it will go in a racetrack type motion forever. Once the process starts, it never stops going around and around and around in this circular motion. And we have 3 separate basins to have a maximum flow capacity.
And when you say oxygen, I assume you just mean ambient air. We're not using industrial oxygen.
No, we're not using any industrial oxygen. It's just compressed air that we have blowers in the building we'll go see. It's just atmospheric oxygen.
And let's take a walk down here. We can look on either side here to see these chambers. Now, what's the distinction between the chambers on this side of the walkway and the chamber on the other side of the walkway?
Well, the chambers here, these smaller ones, this is for some advanced treatment of wastewater. We can recirculate flow out of this racetrack type ditch basins, bring flow back into these small chambers, let the solids settle, and we can starve it for oxygen, which then the bacteria goes after the ammonia and the phosphorus in the wastewater. We have to remove ammonia and phosphorus for advanced treatment. But if you starve it for oxygen, you create an anaerobic situation, and then the bacteria go after the phosphorus and ammonia.
So these will be covered?
No, these will all be open to the atmosphere. The flow stays in here just for a short period, less than a day, then goes back into the process.
So how do you starve it for oxygen if it's open?
Well, you'll have a certain amount that's absorbed, but if you'll notice, these basins have no aeration in the bottom.
Uh-huh. Okay, so let's take a little walk down here. Take a look at the circular form. And why is water spraying there?
They're pumping water out of something.
Uh-huh.
Probably just
so here's one of the, is that pipe connected with?
That's connected underground to the headworks building, and it feeds these, but then again, like I say, we can recycle back into these.
Mm-hmm.
Watch your footing, this is icy. You want to talk a little bit about these red pipes?
Sure, go ahead.
The red pipes behind me are actually the compressed air pipes. That's the piping that's conveying the air down to the oxidation ditches, down to the aeration system down below. And you can see the multiple discs where the air will bubble out of fine bubbles. But that piping goes into is coming from the blower building where our compressors are.
And where are the compressors?
In that next building over.
Okay. You said that this is costing $40 million, what we're looking at right now. How's that paid for?
The treatment plant we're looking for right now, it is right at a $40 million project. And this is being paid, we borrowed the money from the state revolving loan fund, and it is being paid by the rate increases that the city has had to implement in the last several years. But it's basically paid by residential sewer rates. Now it's a combination of also commercial rates in town, industrial rates from our industries, and we also will be charging Comanche and Lowmore to treat their sewage.
And why did we use the state revolving loan fund as opposed to selling bonds on the market?
The state revolving loan fund, when we originated the loan, and this will stay for the life of the loan, the interest rates were lower than the bond market. So that is why we went with the state revolving loan fund. That fund is actually funded by the federal government, and the intent of that is to give cities very low interest rates to build projects such as this. This pipe that's right here by my left, this is one of the pipes coming from the aeration building where our blowers are that are going to provide the air to the aeration basins, to these oxidation ditches. What's interesting is the size of these. This is like a 36-inch diameter pipe. Think about the volume of air that will flow through that compared to like when you go to a gas station to air up your tires. It's a massive amount of air that we pump into the wastewater to feed the system.
How many horsepower are the pumps that generate that air?
We can look at those when we get inside.
Okay.
We'll talk about those inside. Really, it's going to shock you. They're little bitty. But we bought some.
Okay, go.
Alrighty, I'm standing in front of one of the aeration blowers that will provide the air to the oxidation ditches. And you'll notice that this thing's only about 2 foot in diameter. The older technology for blowers, this would have been enormous, but this is a new turbine blower. It spins at 35,000 RPM. And this will be, there's 3 blowers in this building that will provide all the oxygen we need through that 36-inch pipe outside. And you'll see the discharge of these blowers comes, this is the suction side, and it goes up through a filter on the roof. comes in through the blower and then goes out into that header pipe and then goes into the oxidation ditches.
Looks like a pretty good electrical service here.
Oh yeah.
Have any idea what the capacity of that is? And the voltage? It says high voltage, so.
480, 320 amp. You'll notice all technology, when this is running, this is a small screen. It's a touch screen, so we can control the blower, change the speed if we want, or the operator can do anything they want to the blower at this point.
And you mentioned how many RPMs the blower goes at?
35,000 is max speed.
35,000 RPM.
Correct. Left and right here to my left and also over there in this building is all the electrical controls for this building. Controls the blowers, it's the feed for all the blowers, main disconnects. It's also the feed for the pumps that we'll see in the next room. These pumps to my right are the pumps that will pump flow from the oxidation ditches and will pump flow over to the final clarifiers. The flow that comes to here will be the flow that is after that basic treatment. So no funeral.
Okay.
We're standing next to one of the final clarifiers. This is a 120-foot diameter tank, and after treatment in the oxidation ditches, the somewhat clear flow comes over to these basins. These basins are just holding tanks where the water sets for approximately 24 hours, and the mechanism you see on the bottom is a skimmer mechanism that rotates around and collects the solids, the really fine solids that that'll settle out of the wastewater. Those solids are pumped back over to the digesters for treatment, and we'll talk about those in that process. But we have 3 of these clarifiers, and we have capacity to add a 4th clarifier if the city grows or if we have the need for increased treatment.
What is it that actually collects the fine solids? Because I don't see any hose or any intake.
Actually, what you don't see on this left-hand side, you see the aluminum setting down close to the floor. There's a scraper blade that will scrape that to the edges, and then you'll see in that tube over there, the solids literally are collected into that tube, and the weight of the water pushes the solids into the tube. Then it's collected off through this trough into this trough, and then it's piped back over to the digesters.
So this is really for that purpose, and this is not a swimming pool for public works employees.
No, it's not. We're standing in the final lift station, and this is the pumping station. What you're looking at right here is the top of the pump that actually sticks way down into about a 20-foot deep wet well. The electric motor will set on top of this and drive a shaft down through there. That pumps the flow out to the river. This is the lift station that will pump it back to the river after final treatment. The skylights in the roof are not just for decoration. That's how the pumps were set in here. They were lowered by a crane. These pumps are one long shaft. If we ever have to pull one, we have to do it with a crane and pull it through those skylights. Now where we're at is we're inside the solids processing building at this point. We've talked about solids a little bit and how in the oxidation ditches solids are created and through the reduction of the wastewater. And then we've also talked about the solids that we settle out in the settling basins. Those solids are pumped into this building behind me. They first go through these two rotary thickeners, they're called. And these are basically centrifugal thickeners that work just like a centrifuge and spin at high speed, and the solids are spun off the water and concentrated. Those solids then are pumped over to these three rotary presses, which then dewater the solids further down to a point of where you have 24% solids. 24% solids are dry enough you could make a dry mud ball, like a baseball, out of those solids. Those solids are then just conveyed out into this next building for storage and then for land application eventually.
Fournier is the company that came here, when, 2 years ago?
And yeah, did the demo at the plant.
And gave the demo. So we had some prior familiarity with this technology.
Oh, yeah. And I have seen this technology in practice at a couple other wastewater plants.
Okay.
There are a lot of advantage to these rotary presses compared to other technology presses, for example, like belt presses, gravity belt presses, which tend to be really operator intensive. You have to have an operator there. As I was saying, a belt press is very operator intensive. You need operators there all the time. It's also, if the belt gets out of adjustment or the feed gets a little off, you can have the solids literally running off the belt onto the floor, which makes a huge cleanup. The advantage to these rotary presses, you'll see kind of the round chambers. You'll see the round chambers right there. There's 6 separate chambers in each one of these, but those chambers contain the liquid and the solids totally. So there's never a chance of a spill. They're very operator friendly in that an operator needs to check on these every few hours. They pretty much run by themselves. In here we have another blower room. This is again in our solids processing building. But again, we use oxygen that we pump out of the atmosphere into the aerobic digesters that are behind us, and we'll walk by and look at those tanks. But again, the oxygen just helps to consume the bacteria in the wastewater in the digesters. Digesters are exactly what the name implies, it's digestion of the solids.
You say bacteria. The bacteria actually help break down the sewage into other component parts. So normally you want to enhance the bacteria, don't you?
Right, and what we actually do is the oxygen, the bacteria thrive on the oxygen. That's actually the process of feeding them more air to the bacteria. These are beneficial bacteria. It's not like a germ that's going to give you a cold, but this is bacteria that's beneficial, similar to what's in your digestive system. And just by pumping more oxygen to it, just as your body does, you digest that solid material.
Works faster.
That's all we do, is we speed up the natural process by pumping massive amounts of air into it. Just the control panels for those thickeners and the rotary thickeners that you saw in the other rooms. It's just all the electrical main breakers and control panels for that equipment.
So this project is really quite a consumer of control panels, isn't it?
That's true, and everything is on a variable frequency drive. Again, everything is wired together through a SCADA system, supervisory control and data acquisition system.
That's what SCADA means?
Yeah, SCADA is supervisory control and data acquisition. And we've got offices in 3 of these buildings that from any one of those offices, the operator could change anything in this plant at any time just from a touchscreen.
Are we going to have, I thought this was going to be totally automated and we wouldn't have people based here.
There won't be people here full time, but if the flow varies or if for whatever reason you've got a difference in our lab results, we may want to adjust processes. Normally it will be completely automated. It will run by itself. For example, in the oxidation ditches, we have sensors in there that reads the amount of oxygen in it, and then that SCADA system will vary the amount of air that the blowers feed. But if you need to change that because maybe the flow is a little different, flows higher, lower, maybe we got a little heavier waste load in it for whatever reason, you may want to adjust that process a little bit, and you can do that from any of those screens. Southern indentation. This is shower right here.
So this is a locker room, changing room,
locker room,
bathroom.
Just to clean up and change if you need to, if you do get to where the point you need to clean up. We're standing on top of the aerobic digesters. This is the final stop for the solids, which are still, when they come into here, are in a pretty much a liquid form yet. But these digesters, as we've talked, that's where it's further digested. The solids are reduced even further before they go into the solids processing building. There's 4 of these digesters in this complex we're standing on. Yeah, there's 4 separate tanks here.
How many gallons do they hold? How large are they? How many feet long and wide and deep?
These 4 digesters together, I don't have the exact dimensions in mind right now, but I do know they hold 4 million gallons total, million gallons each.
Uh-huh. And what is our throughput estimated to be here at maximum capacity?
13 million gallons at maximum capacity, but our normal flow is closer to 5 million.
Uh-huh.
But we have a lot of room for excess capacity for future growth.
And growth is not necessarily population, but industrial.
Industrial growth. And industrial growth, well, it leads to growth in 2 manners. If we have a fairly large industry, we can get a lot of waste, a lot of flow from that industry. But that also stirs a lot more population, so then we get that flow from them too because of growth.
Now, looking over here is a view from this vantage point. This is the initial building here, right?
Yes, that's the headworks building right there where the flow comes in initially. Then you can see the oxidation ditches. And then past that is the secondary building where those blowers were and the pumps that go into the final digester, or the final clarifier.
Where the tall crane is.
Correct. When this is the again the solids storage building, that will have a concrete floor, and what you're looking at in the middle is just a trough that will collect any water that might seep off of it.
By the way, earlier you mentioned that the normal flow is about 5 million gallons a day.
Correct.
What is the flow when we have a storm event?
Well, an oxidation ditch is very flexible. We will never exceed 13 million here. And we can talk more about that when we get back to the existing plant.
Okay.
Right here.
So this is where it goes under Mill Creek, huh?
This is the pipeline coming that's going to go to the new plant, and we bored under Mill Creek.
Okay.
And they're getting ready to do another bore over there that's going to go down to the outfall of the plant.
That's a problem there. Okay.
What we're looking at right here is going to be the future pump station. That pump station goes almost 40 feet in the ground. There will be a building over it eventually with pumps and controls in it, but that pump station will pump all the flow from the city out to the new treatment plant through this new piping system that went under Mill Creek.
And how much is that costing us?
This is part of the 40 million.
Oh, it is part of it?
Yes.
And what are we looking at here?
This is part of the existing plant, and this is just the grit removal system. This is the old style that you used to use for removing grit.
Now, will we continue to use this when the new plant is open?
What you're looking at here is these primary settling basins on the existing plant. Different type technology, much older, but you can see the difference in size of the tanks between this plant and the new plant.
Well, part of the difference in size is because of the different things we have to take out of the effluent.
The difference in our permit limits, correct. standing in front of the existing treatment plant. This treatment plant was designed and built in the early 60s. And it was designed and built to meet limitations that the EPA and DNR had on our effluent back then. Over the years, those limitations and on our effluent have gotten much more stricter, and we also have to remove ammonia and phosphorus from the waste stream. We started looking at that when those permits were coming in about 7-8 years ago, and thinking about, well, we'll have to modify our existing plant to treat wastewater to those limits. This existing plant is somewhat landlocked though, and we could have added on and modified this plant for an estimate of about $20 million, and that would have met current limits. The problem with doing that though is it would not have allowed for any growth in the city whatsoever, because we were still at our maximum hydraulic capacity. So we got to looking at that issue and the city decided it would be best, if we're going to spend $20 million, do we need to start looking at maybe a new site? At that point, we also started discussions with the city of Lowmore and the city of Comanche, and the city of Clinton was also starting to develop the rail park. So when we looked at all those factors, the city decided that it was wiser to just build a brand new facility that would suit the city for the next 50 years, just as this plant has. Now the good thing about keeping this plant here is we have all of our wet weather issues with combined sewers in the city. We've been meeting with the DNR and EPA that we will convert this plant in the next few years to what's called a wet weather plant, so that we can minimize the cost impact on collection system work we have to do. That means we had an early estimate of nearly $180 million in the collection system. By creating a wet weather plant, that may save us nearly $80 million of that 180.
The 180 included the cost of the new plant?
No, that 180 was just collection system work.
Only collection
Only collection system. So by utilizing this as a wet weather plant, in other words, when we get our flow coming here, we'll be able to pump up to 13 million gallons out to the new plant. That's the maximum hydraulic capacity of that plant and the effective treatability. Anything above 13 million, and we often go well over 20, anything above that 13 million will come to this plant as a combined sewer overflow and just get minimal treatment.